Hi, everyone. My name is Aurelio Muraca. I'm the Technology Program Coordinator here at the Danbury Library. On behalf of the Friends of the Danbury Library, we welcome you to our new updated series of Earth in Crisis, with episode one being Ice Ages. And without further ado, I present Professor Mitch Wagener. Thanks for being here and always being part of this series and educating the public about the effects of climate change.
Thank you for inviting me. It's always fun. I do quite a lot of these, and it's a great source of enjoyment and satisfaction to me to be invited back. And so I'm happy to be here.
We'll always have you here, Professor Wagner.
Well, what we're talking about today is ice ages, and ice is one of the most obvious types of surfaces one might see if you were orbiting the Earth in a spacecraft, or if you're looking at pictures of the surface from a satellite, because those areas of the Earth's surface that acquire more snow than melts every year will gradually build up into what we call ice sheets or glaciers or ice caps or so on. And you find them in places that are cold, obviously. Okay. So the ice caps that are most obvious from space are the North Pole ice cap in Antarctica. Antarctica is the topic of another talk later on in this series. Um, but you also see others, and you see, of course, in the winter in each hemisphere, the areas that are covered with ice are and snow are seem to move a little farther toward the equator temporarily. All right. Now, this ice is immensely important because it's reflective. And the more ice there is on the surface, whether it be on the top of Mount Kilimanjaro, such as we're seeing here, or it's on floating in the ocean, or it's on the continent of Antarctica, or wherever happens to be, it reflects light. It's said to have a high albedo. Albedo is the ability of a surface to reflect light. So bare soil has a low albedo. It absorbs more solar radiation than it reflects, whereas ice and snow um, will reflect it. And so as we, talk about in the coming weeks, the melting of polar ice and Antarctic ice, we're talking about the replacement of a reflective surface with a much less reflective surface, and anything that's not being reflected is that energy is being absorbed. And so it's a big deal, and it's one of the mechanisms by which the Earth can warm and the Earth can cool. Now, this picture is Mount Kilimanjaro, the highest mountain in Africa. It's a volcano, or it was at one time. There's three caldera on the top. And there was a time when there was quite a lot of snow up there. In fact, Hemingway wrote his novella, The Snows of Kilimanjaro, referring to that. If you were to, in this picture, notice the pictures of Mount Kilimanjaro also always have wildlife in the foreground, either a giraffe or an elephant or zebras or whatever. At least the ones taken for tourists do. And you can see that there is a snow line, and that is the point um, beyond which more snow falls than melts long term. And below that is more snow melts than falls. All right. So this is, something that's very important, and we will be talking about um, how those periods in Earth's history where much more of the Earth's surface is covered with snow than the average, and how those things called ice ages begin and end. We have lots of evidence of ice of the last ice ages around here, which we'll get to in a bit. Oop. Oh, come on. Is two. All right. So, Mount Kilimanjaro, among the tallest freestanding mountains in the world. My wife's brother, who was a famous geologist when he was a young man growing up in East Africa, uh, hiked it to the top. I've never been there. I certainly hope to be able to see it from the plane. 4,600 meters from its base, and there are three volcanic cones with Swahili names. And the mountain is near it's in Tanzania near the border with Kenya, if you're interested in going. And the Serengeti plains are around it. All right, now glaciers in general are an important thing. They are the largest pool of fresh water on Earth. The largest pool of salt water, of course, is the oceans. Um, There are a number of different kinds of glaciers. There's alpine glaciers, there's tidewater glaciers, there's ice sheets. Alpine glaciers are those that form, like on Mount Kilimanjaro, up where it's cold on top of mountains. It's cold because of altitude, not because of latitude. Um, Alp or tidewater glaciers are those areas in the north and the south, in the cold parts of the world, where more snow falls than melts. And so the ice will then, that forms from the compacted snow, will melt, will start moving downhill. You don't think of ice being a solid as moving, as flowing, but it does. And, it's just water. It's just water that's linked together in a different way. And given enough time and given gravity and given a slope, it will move downhill. And so those areas where you have a lot of snow and it's pretty cold, like Glacier Bay National Park in Alaska, the ice will flow down from the mountains in inland, and it will then chunk off into the ocean. Now, I've seen ice chunking off from a small glacier chunking off into the Copper River, which is just north of Prince William Sound. And makes the most amazingly fantastic sound you can imagine. It's a bass that just causes your guts to vibrate. It goes all the way through you, and you just feel it as much as you hear it. All right, ice sheets, on the other hand, are much more long-term ice that are in an area that is high in altitude, sometimes like Greenland, and high in parts of Antarctica, and high in latitude, meaning closer to the poles, and they pile up lots of ice that is melts some on the edges of the surface every year, but there's more snow that comes in the winter. Okay, the mass balance of how much is coming in and how much is going out is part of the important story about that. Oh, come on. All right. So a glacier then form where the accumulation of snow exceeds the ablation. Ablation is the geological term for the combination of both melting and evaporation. Another thing you might not think of until you think about it is that ice and snow can go all the way from the solid state to gas, water vapor, without passing through water, without passing through liquid. And I remember as a young lad and growing up in Missouri, you'd get a little snow and I'd go out and sled, and the next day it'd be gone. But it didn't seem to melt. It just seemed to disappear. And I always felt cheated. Maybe that's why later on I moved to Alaska. So ablation is melting and evaporation. And if you are gaining more snow than you're losing, it's going to build up. If you're losing more than you're gaining, it's going to disappear. It's kind of like your bank account. So the growth or disappearance of a glacier is a process of mass balance. Now, this is a um, a springtime photo of the surface of the ice sheet in Greenland. Before the summer worth of dust and stuff trickles on it and makes it all grungy, and before the lakes melt in the surface. About 16,000 years ago, this is what Connecticut looked like at the end of the last ice age, which we'll talk about later on. One of the really spectacular things about ice is that for the same reason that really clear water, really clean water, such as Lake Tahoe and some areas of the ocean are blue, the deep blue sea, as the phrase went, are blue. Ice is blue as well if it doesn't have a lot of impurities in it. It's blue because the hydrogen oxygen bonds in the water molecule will absorb red on the red end of the spectrum, leaving the blue as scattered away. You add a bunch of muck to it, algae or turbidity of any kind, and you lose the blue. It turns more into, well, greenish brown or something like that. But you look at sometimes in Alaska when you'd see the river ice melting in the spring, and you'd see bits of the off ice that flows that is on the bank that is the leftover of the winter's ice. You'll see, little patches of blue from really, really clean ice at that spot. It's really spectacular in the sunlight. And as I said, the ice will in fact flow downhill. And as it does, if you find ice that's high altitude and you fly over it with a helicopter or whatever, you'll see flow marks, stretch marks, if you will, in that ice, and you can see how one patch of ice from one direction will flow against another patch of ice, and it'll flow together and form a common flow. And it looks like rivers moving together, and they are, in fact, rivers of ice, but they're moving a lot slower than the rivers that are made out of liquid water. Now, one of the things about Earth's history, going back to a a time before animals appeared, Um, the Earth's surface has cooled and it has warmed up repeatedly over long periods of time throughout Earth's history due to processes which we'll talk about in a minute. There was a time right before the Cambrian, right before animals appeared in the fossil record, that the ice almost went all the way to the equator in both the north and the south and left just a little stripe of unfrozen territory um, around the equator. That was called a snowball Earth. Geologists talking about that particular time. And there were other times that were almost as severe, but not quite. But ice ages are when you have an extension of ice that moves much farther south than it usually is. At the end of the last ice age, the Pleistocene ice age, you can see the white here is where the ice stopped. The further extent, the glacial maximum, as scientists like to say, we like to come up with complex, sometimes poetic words for things. The glacial maximum at the end of the Pleistocene, which was 16, 18,000 years ago, is not very long ago, was here. And you can see important things here. For one thing, that white is the ice. And when you have a bunch of water, of the Earth's water, up on land above sea level in a big ice sheet, that water is not in the ocean, and so the sea level goes down during an ice age because the water is up above sea level. And so you can actually, if you look at carefully at the edge of the continents in this map, you can see that it was really different. Look at Florida. Look how wide Florida was relative to its shape now. Look how the British Isles, Ireland and Britain were one and were connected directly to the European mainland. Notice how Sri Lanka, that island off the southern coast of India, was part of India. Look at Southeast Asia. Okay, the western half of the East Indies, pardon my dog, um, were connected to and of a piece with the Asian mainland. Ringo saw the neighbors across the street. He's a terrier, can't help himself. All right. So you see then that the western part what is now Indonesia and Malaysia and Thailand and so on were all part of the Asian mainland. Notice how New Guinea was connected to Australia. And very importantly, notice how Asia is connected to North America, although you have to kind of wrap your vision around a little bit so you can see it in the land bridge. Okay. During this time, when those areas were above sea level, organisms could move back and forth across them, including humans. That's the time when humans from Asia, Eurasia, basically walked across and and basically parked themselves, lived in an area called Beringia, named after Vitus Bering, but that's a different story, um, in central Alaska, but they couldn't go any farther into the New World unless they had the technology of boats. And a few people did, and they could kind of go on the southern edge of the ice sheet and move on down earlier than most of the Paleo Indians did. So they just basically would hang out there in that zone. And not only were they there, but all the animals that one associates with the polar ice, or pardon me, the ice ages, like woolly mammoths, which are my personal favorite, and woolly rhinoceroses, and all sorts of other things, which we'll talk about in a bit. As the climate began to warm up again, at the end of the glaciers, ice started to melt at the edges. The ice sheet covered less of the land surface. That water runs into the ocean. The sea levels come up, and we have the shape of continents we're more familiar with today. Ice ages. Now, there are big ice ages and there's little ice ages, ones that last a long time and ones that are relatively short. There are really particularly severe ice ages and some that are barely worthy of the name. There are within a long ice age, there are shorter temporary warming periods called interglacials or interstadials. Okay. Within a warm period, you can have a something close to an ice age, but very short, called a stadial. So there's all this terminology that refers to, whether it's a short time or a long time, whether it's a severe cold time or whether it's a not so severe warming time. Okay. And geologists, will revel in all this stuff. I'm not a geologist, I'm an ecologist, but I still think it's pretty interesting. If we look back at Earth's history for the last 542 million years, since the appearance of animals in the fossil record, we use the animals in the fossil record as an important milestone because, after all, we're animals on themselves, ourselves, and When you have animals that have bones and shells and hard parts that fossilize, they start showing up. It could be that there were some soft and squishy jellyfish-like things before, but they didn't fossilize because not having hard parts, they wouldn't as often. And you can see here the um, the recreation of the temperatures into warmer times and cooler times, and you see the glacial periods that are marked with the blue rectangles at the bottom. Now, how do we know that, how hot or cold it was back in the end of the Ordovician or the Silurian or the Carboniferous for that matter? Well, we're able to take samples of a known age determined by the isotope signature of the material, okay, and where it's found in the stratum. And we're able to analyze it for a particular isotope of oxygen. A particular oxygen has three main isotopes, I guess. The isotope, by the way, is an alternative form of a atom. The one that you and I breathe in and is the by far the most common is oxygen 16. Okay. Oxygen 16 is not radioactive, which is good. Otherwise, it wouldn't be very good for us. There is oxygen 17, which has an extra neutron, but it's not radioactive either, but it's a little heavier. And we have oxygen 18, which has two extra, and it is something that, because it is heavier than oxygen 16, it tends to be indicate let me get this right before I don't screw it up. It indicates a cold climate at the time in which it is found. Okay. So the relative amounts of the ratios of oxygen, and there's other ratios of other elements that tell us other things. There's, carbon isotopes and all that. Well, the way we determine is by looking at these isotopes, largely in ice sheets, cores of ice sheets that uh, have little ringed layers, kind of like the tree rings on a piece of wood. And of course, scientists have to come up with names that nobody else can remember, like the quaternary and the cryogenian and all that stuff. So don't worry about this. But there are different ice periods, and with a relatively um, approximate time interval in which they were found, and within which other more famous time periods we can place them because scientists need to be able to put things in a structure of time so we can understand what happened when. And if we look at from the formation of the Earth on the far left of this rectangle to now, and then the far right of this rectangle, those areas that are labeled in light blue are those areas that were had a lot of particularly ice ages in them. All right. Now, how is it, in fact, that the what is it that pushes the Earth to an ice age and pushes it back out of an ice age? And the answer to this is a whole bunch of things, but three main drivers. And together they're called the Milankovitch cycles, named after some bloke named Milankovitch, no doubt. And they are geology scaled in time changes that either tend to warm or tend to cool the earth. And if you have all three of them cooling at the same time, you get positive feedback systems, which then push us into a cooling phase. And if they're all in the warming phase at the same time, they push us into warm side of this. And they are eccentricity. I'll define that for you in a minute. The axial changes in the axial tilt of the Earth and the precessions of the Earth's orbit. That's the wobble of the Earth's orbit or the Earth's spin. And I'll explain that here. Each one of them changes on its own cycle from warm to cool. Eccentricity is the longest one. That's the shape of the orbit of the Earth as it moves around the sun. And a precession is the shortest one. But, put them all together and they will collectively make us warmer or make us cooler for longer or shorter periods of time. Now, orbital eccentricity is this. Earth's orbit around the sun is an ellipse. It's an oval, not a circle. And that's because the big gravitational forces out in the outer solar system, Jupiter and Saturn, exert a tug on the Earth and pull it slightly out of its circular orbit. Okay. And the eccentricity is the departure of the ellipse from circularity. That's what that means. Of course, scientists can't say anything simple. They got to turn it into some fancy schmancy word or term. So you can measure, and scientists do measure the eccentricity of an orbit, and they give it a numerical value based on where the sun is in the orbit and how different that orbital shape is from circular, pardon me. And so the orbit as a perfect circle and the sun at right dead in the center is eccentricity of 0, and the one on the right, by contrast, is 0.5. Okay, the ways of analyzing this so we can see what's going on. And so the Earth's eccentricity, because of the big planets, varies between two numbers, and this component varies on a cycle of 413,000 years, and there's other minor components, and it's some of the um, of the other planets are much more circular in orbit, such as Venus and Pluto, which isn't technically a planet anymore, is very elliptical. Anyway, so let's see, I can probably. Now, the odd thing here is that the distance of the Earth to the sun changes, but the speed of the Earth as it moves around, the length of the year doesn't change. And the perihelion is the Earth's, what the name for the Earth's nearest approach to the sun, and the aphelion is the farthest. And the difference in distance of the Earth from the sun is only 3.4% between the closest approach and the farthest. But that's enough to vary the solar radiation reaching Earth at 6.8%. So and so basically what we have is something like this, where we have the Earth going around in this ellipse, and we have aphelion is occurring, which influences the whole thing, and perihelion is, so it's scientists get into this stuff. Let's see. Now the second thing that will, or as a component of the Milankovitch cycles, is the axial tilt. Back when the Earth was hot, before it was cooled to be a real solid, it was kind of a cooling ball of really hot rocks. At about that time, another planet, one that it was about the size of Mars, that scientists call Theia, slammed into the Earth. And in so doing, it did some very important things. One of which is that object, Theia, got consumed inside the Earth and is below our feet even today. The force of that knocked part of the Earth out and separate, which became the moon. We know that the moon is of similar material as the Earth because we've been there and collected rocks and we did the analysis and all that stuff. But the things that occurred through that collision, one is that the tilt of the axis of the Earth relative to where the sun is tilted. And so it varies, and that tilt is not constant. It changes between 22.1 degrees relative to the sun to 24.5. And it's currently, last time I looked, 23.43693 degrees. As many decimal points as you want. As the angle gets larger, the amplitude of the seasonal cycle increases. Summers are warmer and winters are colder, to simplify things. And this is on a 41,000 year cycle. Okay, there's that. And the axial tilt changes between those two values currently. Now, the third is the axial precession. And likewise, when Theia slammed into the Earth and was consumed and became part of the Earth, it made the Earth not uniformly dense. And so it gave the Earth a wobble. And so when the Earth spins, it changes, it wobbles in the spin, like putting taping a coin to the inside of a playground ball and spinning it, and you'll notice it wobbles. Okay. And because the Earth is not a perfect sphere. And this is on a 26,000 year cycle. And so you remember in Boy Scouts where they took you out on a camping trip and they pointed to the clear sky and told you, maybe Girl Scouts did this too. They told you how that you could find what we call the North Star, and that if you follow the position of the North Star Polaris down to the horizon, that's north. That's true now, but it won't be true forever, because as the axis of spin wobbles, the star to which it points changes. So if you look at this little illustration on the bottom left, you can see that right now Polaris is the closest bright star to the northern horizon, but in 10,000 years it'll be Deneb, and in 14,000 years it'll be Vega, and so on. Be a different star. We'll have to retrain all the Boy Scouts. That too affects not the North Star, but the wobble affects which areas of the world get more solar radiation at any given time. All right, so you put them all together, and if you get all the warm cycles hitting, you can shift into out towards a warming time. And if you get the cool things hitting together, you may shift us into, in fact, a ice age, but only temporarily. And so, you can take the data as observed, not as projected, but observed from our proxies that tell us how things were in the past, and look at the precession, look at the obliquity, and look at the eccentricity, and throw in changes in the solar radiation over that time. And they predict pretty well when in the past we've had ice ages and when we've had interglacials. So we know that this is a reasonably good predictor for such things. All right, so the last glacial maximum, 20,000 years ago, extremes persisted for several thousands of years. And the climate in the glacial world at this glacial maximum, at this high point, the largest extent of ice in the last ice age, was about 4 degrees Celsius colder than today on global average, a little bit colder. So would you notice it on a day? No, you wouldn't. But it all that heat piles up and all the lack of heat piles up sort of negatively. Okay. The North Atlantic was actually 8 degrees colder. And because more of the world's water was tied up in ice, it was drier. There was more sea ice, and sea levels were 120 meters lower than they are now. And the shoreline of North America looks something like this. At the peak glacial, the light blue, and the peak interglacial, um, the warmest time between the ice ages, the shore was the dark green. Oh, come on. I always hit the wrong button. All right. And during the most recent ice age, the dark line shows you how far south the edge of the ice sheet extended. A previous ice age from before this last one gave us the little dotted line that went through the middle of Missouri. In fact, that line traces pretty closely the current channel of the Missouri River through Missouri. I grew up in Missouri, so that's all familiar territory to me. And because we can go in and take cores of ice from Antarctica and Greenland and we can analyze them in an appropriate way, and because a year's ice is in a layer which is visible so we can see what's going on, we can we can put together the glacial history of the Earth for the last half a million years or so. And since there's traps, bubbles of air, atmospheric air that are trapped in that ice, we can analyze that and get an idea of what the mix of gases were at that particular time. And yes, you would expect there to be more carbon dioxide during the times that were the warmest, or conversely, that it's warmest when we had the most CO2 in the atmosphere. All right. I already mentioned this. I guess I should edit my slides better. Now, let's talk something about what the environment was like at this last peak of of um, of, of ice. Well, the sea level was low, and therefore that area, the two peninsulas, which are Chukotka on the Russian side and Alaska on the North American side, were together because sea level was low. Okay, critters could go back and forth. Humans went back and forth. Okay, and that area is called Beringia now after Vitus Bering. Well, that's a different story. Um, and that isthmus that was formed there temporarily, a land bridge, was 1,600 kilometers north to south. The environment that was there on that was largely a something that it's a non-analog to anything we have here now, really. Okay. Um, we can estimate what the vegetation was like because it did in fact support lots of big animals. And it was something we call steppe tundra. So it's a combination of grassland with permafrost in patches and stuff. And Beringia, that big grassy area, was a refuge for organisms that were in the process of hiking from Asia to America and couldn't go any farther because of the ice blocking their path. A refugium is the way scientists talk about it. And the isthmus, the land bridge, looks something like this. Doesn't look like that now, but it did then. And 20,000 years ago, you can see the current boundary of the two continents there um, marked. And within that, what was then the land bridge. And 15,000 years ago, the ice, enough ice had melted and enough sea level had come up that the two continents were then Chukotka Peninsula and the Seward Peninsula and Alaska were separated. And today, there is a significant amount of water between. There are two places in Alaska where you can actually see Russia on a good day, and two, just for interest. One of them is there's an island, a long island going east and west in the Norton Sound there, south of Chukotka and Seward Peninsula. It's called St. Lawrence Island. Pardon my dog. St. Lawrence Island, and it's on the Alaskan side now, and people live there are Siberian Yupiks. That's the ethnic group because of the language they speak. And on the far western Cape, on a really clear day, you can see Chukotka. You can see Russia. There's also two little islands right in the middle of where the two points come together, and they are called Big Diomede and Little Diomede. That's what the Americans call them. The Russians call them Ratmanova and Krusenstern Islands. And the little island is on the American side, the big island is on the Russian side, and there's Inuit living on the American side, and they can see Russia occasionally. So if you're interested in that, there you go. So steppe tundra, the area that supported lots of big animals and by extension humans that were relying on them for food and and furs and all that stuff. It was about 50% ground covered by plants. It had lots of bare ground too, and there was lots of permafrost in spots. It was mainly herbaceous plants, non-woody, kind of like a prairie, a spotty prairie, a prairie going bald. How do you like that for an acronym, for an analogy? A few shrubs, a few stunted trees, and it supported the megafauna, the Pleistocene megafauna. And the Pleistocene megafauna were things that will be familiar to you, not because you've seen them, but because you have seen them depicted. So we have in the back there a whole bunch of elephants. They are in the family of elephants, and they are of the genus Mammota, the mammoths, big, shaggy, woolly mammoths. And there were a fair number of them, and anytime anybody excavates something in Alaska or Siberia, where there's permafrost, you're likely to find bits and pieces of mammoths and stuff. In fact, I have a chunk of woolly mammoth ivory, fossil ivory, in my office that some guy gave me in Russia once. Anyway, there's also mastodons, which were another elephant, different genus. We see you see in this diorama, you see a caribou, which are still around. You also see American lions, relatives of the African lions and the Asian lions, but ones that could live in a Arctic environment. And if we can find anything that is roughly similar to what steppe tundra might be like, there is a patch of ground on a hilltop not too far from Fairbanks. I remember it. It's in an area where I did some research that may be something similar in looks. This grassy area here is something like what steppe tundra might have been like. So, woolly mammoths. The last woolly mammoth, by the way, you might be interested to know, lived on Wrangel Island in the northern part of, or north of the Russian side of the land bridge, and the island's still above water. And it had a subspecies of dwarf mammoths, if that's not an oxymoron, kind of like jumbo shrimp, dwarf mammoth. And the last species of woolly mammoths died out about the same time the old kingdom of Egypt was building the pyramids. So within historic times, I mean, well, sort of historic times. There was also another, and honestly, if I had a time machine, if I had a TARDIS or something, I would love to go see a woolly rhinoceros because there were rhinos that lived in this environment too, and there were shaggy rhinos. And there are American Alliance and Pleistocene horses, which might still be around in the form of the horses, the Przewalski's horses that are found in Mongolia. Steppe bisons, which are close relatives of the American bison and the Eurasian bison, and then the giant short-faced bear, which is an impressive beast. Woolly mammoths. I'd pay real money to see a woolly mammoth if I had real money. Isn't that cool? I mean, that's just, a big, shaggy, hairy elephant with great big old tusks. And here is a rather unkempt, shaggy, uh, woolly rhinoceros as well. Here's a Przewalski's horse. No, here is a Pleistocene horse depicted on one of the great caves that were painted in the Pyrenees in Europe by artists of early human artists who were depicting, probably bragging about their hunting exploits, and did some spectacular artwork. And one of them was this horse. Now, these were guys, I assume they're guys, that were, but there might have been women, I'm sure would be artists too. I don't know whether they would have talked about hunting kills or not. Notice how the legs of this horse are drawn. So do you know which ones are the ones on the other side of the body relative to the viewer? I mean, that's pretty clever artistry in my mind. Not that I know all that much about art. And here's a steppe bison, or the and this is from a different cave, Altamira, I think. And one of my goals in life after retirement is to visit this area in the Pyrenees between France and Spain and see some of this art. And here's the size of a giant short-faced bear relative to, the average schmo with the pointy stick. I don't think it would be much of a fight. All right, so in the late glacial maximum, 10,000 to 13,000 years ago, the climate was warming. We had an acceleration of deglaciation, ice was melting. And that at some point, the passage that allowed humans to migrate into North America moved through. By the way, camels and horses, I think I'm right there. I know about horses, evolved in the New World, migrated over the land bridge into Asia, and then went extinct in the New World and didn't appear here until Europeans brought them back over much later. But at this time, because of the change in the climate, a lot of the big animals, the Pleistocene megafauna that were adapted to cold temperatures were not able to survive, and so they went extinct, with some exceptions. And about 21,000 years ago, this was the edge of the ice sheet. Notice that it correlates nicely with the Long Island. Turns out that Long Island is a landform that was created as the ice sheet extended at the beginning of the Ice Age, forming a terminal moraine. And ice sheets now, like we see in Antarctica, like we see in Greenland, will flow down to the sea level and they'll extend out over the water. They'll lose contact with the bottom, allowing water to flow underneath, which speeds up the thinning of the ice, breaks off into icebergs. and float away. And so one of the two ways in which sea level can rise, one is warming of the water. Two is the addition of ice or liquid water, meltwater to the ocean. And that's why the sea level goes up during the warming phase of this cycle, or in our case, and happening much quicker, um, because we're tinkering with the chemistry of the atmosphere. And so you get big chunks of water or ice chunking off, making crazy bodacious sounds. And the ice that covers up on land then melts in place. It does not pull back. It can't pull back because there's nothing to pull it. And it just melts in place, and the water will form these braided streams that will flow down into the ocean, and it will leave behind its moraines, the terminal and lateral moraines, and the chunks of ice will form kettle lakes as they melt, and you have the Connecticut landscape, and it's where the stone walls come from. Um, Before the last ice age, the Green and White Mountains in Vermont and New Hampshire were as tall as the Himalayas are now. But four episodes of glaciation after that caused the ice ground those mountains down to nubs that are certainly lovely mountains to hike in and ski down. Uh, and the chunks of those mountains were carried here and rounded off and deposited here when the last glacier melted. And then um, the European farmers that came here and farmed the land and had to deal with the frost heaving of these stones to the surface, built walls out of them. And that's where I end my story.
Thank you, Professor Wagner. Do we have any questions? If you have any questions, please put it in the chat and I can relay it to Professor Wagner.
Can I anticipate one question that someone might ask? Is that how do we know that the warming that we're encountering now isn't just one of these Milankovitch cycles? Well, and I've heard this before. I mean, it's a reasonable question to ask. And the answer to it is that the process of warming that you find via the Milankovitch cycles that cause ice sheets to ebb and flow um, occur over hundreds of thousands, tens of thousands, and hundreds of thousands of years. The warming that we have noticed since that is causing us concern now has all happened since 1800. And so the current warming is much, much, much faster than you would ever expect from causing by glaciers. Okay, that's it.
We have a question from Bill. How can it be determined that the ice sheet was 1 mile thick?
Probably from the mass of the ice and I'm just guessing. I'm not a glaciologist or a geologist. I'm guessing from the amount of water that flowed from them into the oceans and how much sea level rise they caused, and also by, that thick layer of ice is massively heavy and distorts the geology and the landforms below it. I think that probably gives us clues as well. That's the best answer I can give you.
Great. Another one from Bill. Is the current cooling a Canadian response to the tariffs?
Well, it's the Arctic, the polar vortex. There's the distortion because the Arctic air mass is warming faster than the other air masses. There's a distortion in the polar jet stream, which is allowing the cool air to come down and some of the warm air to go up, and it's getting all wibbly wobbly like that. And so that's why we're getting all this really cold. Somewhere to the west of us, it's it's surprisingly warm up in the Arctic.
If you have any questions, oh yeah, can you quickly recap the origin of our moon?
Oh,
I'm
okay.
blown away by it.
So, early Earth, hot rocks. The an object about the size of Mars comes in and slams into the Earth. Okay. The force of that object slamming into the Earth and the mass of it, which is consumed within the Earth, pushes out two chunks of Earth, which were two moons we had, which gradually came together by their mutual gravity and became Luna. Cool, huh? Thea is the object, Theia. If you want to look up that in Wikipedia or something, you get more information. But it's a cool story.
Wow. Do we have any more questions? I have a question in regards to like the woolly mammoth or woolly rhinoceros. Did they ever find any of them intact with flesh and fur in the ice somewhere?
Yeah, in fact, it's more likely to find a calf, a young one, a baby, because they're smaller. And in fact, the Russians found a immature woolly mammoth that had been frozen into an Arctic lake and was incorporated into the permafrost. And they dug it up and they curated it and turned it into a museum specimen. And they named it Lyubov, which is a common girl's name in Russian, means love, and they call her Luba. So we have a specimen called Luba.
Question from Bill, is the musk ox a megafauna?
Yeah, yeah, all those animals that are, I mean, technically, yes. I think there's a definition, and ground squirrels are not megafauna. But the things that are big, and I don't know what the upper or the lower limit is for size that qualifies as megafauna. But musk oxen is definitely the extant megafauna that are still around. I saw one in the wild in all my years in Alaska. He was walking underneath the oil pipeline heading towards to the south. There you go.
Do we have any more questions before we end?
Really
Um,
quick, is the megafauna mostly because the bigger you are, the less surface area you have based on mass, so that you can withstand the cold better?
Well, that's part of it. I think a larger object has less surface area relative to mass, as you say. And so since you're losing your heat from that, being large and being hairy are both adaptive traits. So yeah.
thanks so much. We're going to have to end our presentation tonight because it's a little past 7. Just wanted to thank everyone for joining us this evening. Just to let everyone know, the next Earth in Crisis, episode 2, Antarctica, it isn't what it used to be, will be on February 19th at 6 p.m. So if you haven't, please register for that. The more people we get, the more we get to have Professor Mitch Wagener to keep coming back and everything. So once again, thank you, Mitch Wagener, for again sharing your great knowledge and your expertise on this subject and sharing it with us for free via the Danbury Library. This is a great partnership between Danbury Library and WestCon by the biology department, and we want to keep this thing going. So please, folks, drop us reviews, register for our workshop, our presentations for Earth in Crisis. Keep it coming. Thanks a lot, and we'll see you next time.